aircraft are almost here. In designing them, in planning their components, in testing them, aerospace engineers are faced with many new ideas and problems. The Federal Aviation Agency is, therefore, seeking to identify beforehand those improvements necessary to sustain an acceptable level of air safety. The engineers of FAA continually assess the technological limits of safety and aggressively seek out those advancements which offer significant promise. One of these reviews, which revealed many possibilities, was the Transport Crash Safety Project. A key part of this effort, done jointly with industry and the military, involved crashing two worn-out civil transport aircraft as heavily instrumented test specimens into typical ground crash conditions. Many questions needed answers. How can survivability be increased? What are the loads and accelerations inside the aircraft during a crash? What happens to fuel when tanks are ruptured? The first test, the crash of a DC-7, demonstrated the feasibility of the test technique. It also encouraged the test engineers to include an even higher degree of instrumentation and a greater variety of experiments in the second test. As soon as the dust of the DC-7 test had settled, reduction of data began, and the results were incorporated in the Lockheed Constellation Model L-1649, which was being prepared for its crash. Shown schematically, the Connie was to accelerate down a runway, one specially designed with a monorail to guide the nose gear to the precise impact point. Barriers were designed to drive the main gears up and back. An earth mound on the left would simulate a wing-low landing. Two pole barriers would impact the right wing in the same manner as trees during a crash in a wooded area. Based on the experience gained in the DC-7 crash test, the angle of the first slope was lowered from 8 to 6 degrees, so that the fuselage would crest this obstacle without any major damage. The 20-degree slope was designed to stop the aircraft, providing a second and more severe crash impact. A grid system at the impact area, marked in 25-foot increments, would help the correlation of photographic data during the crash impact. Main gear barriers were constructed of railroad ties and filled with concrete. To provide a more realistic effect, no attempt was made to wipe off the propellers. Dyed water was used to fill all the fuel tanks to eliminate post-crash fire and yet obtain information on fuel dispersion. A small auxiliary tank provided fuel for the 4,000-foot test run. The water in the mid-wing tanks was gelled to a thickened consistency. This experiment was to study the ability of this gelled solution to reduce misting of fuels under crash impacts. This gelled liquid was dyed bright red and placed in the center fuel tanks. The plain water was dyed green for the outboard tanks and yellow for the inboard tanks. These colored liquids would help differentiate the spray patterns from the various fuel tanks. 3 types of measuring instruments were used on the aircraft. Pressure transducers to provide fuel containment information, accelerometers to determine environmental conditions, and load or strain links for use on lap belts, seat legs, and cargo tie-down systems. 3 data recording systems were used. Primary data acquisition was done with a magnetic tape recording system aboard the aircraft. More than 80 channels were used. This was backed up with a secondary magnetic recording system also on board. The third source was a telemetry system which transmitted cockpit environmental data. Exterior photographic coverage was obtained from 14 different camera locations and at speeds up to 500 frames per second. 17 specific experiments were on board. The principal ones were cockpit crew seats with instrumented anthropomorphic dummies, forward-facing high-density seating in the forward cabin, a child restraint system, 2 cargo restraint tests, forward-facing seating located in the mid-cabin, also 2 rearward-facing seats at the same general location, 2 experimental litters containing dummies and restraint systems, experiments in the aircraft galley, a side-facing seat, and an aft cabin forward-facing seat experiment. The aircraft was operated in normal takeoff configuration, with the exception of the flaps. They were positioned full up to reduce lift and drag. Throttles were at a predetermined power setting. The aircraft accelerates smoothly. It reaches a velocity of 112 knots just before the gear barriers. At impact, both main landing gears are broken off. As the left gear fails, it rolls number 2 engine down under the wing. The right gear bounces upward into the path of the right horizontal stabilizer, shearing the vertical fin. Visible rupture of the wing structure begins as the propellers and engines drive into the ground. The left wing strikes the earth barrier, shatters the wingtip, and begins to separate from the fuselage at the wing root. The right wing impacts the pole barriers and opens the wing 25 feet from the tip and between engines number 3 and 4. The aircraft slides easily up the 6-degree slope and crests it without any major damage. But impact with the 20-degree slope produces 2 fuselage breaks. Aft of the cockpit, between fuselage stations 370 and 380, and aft of the galley, between stations 1020 and 1030. Now let's move the plane through the crash sequence again to realize the size of the acceleration forces, the G-forces, on the fuselage during the 3 major impacts. First, the forward or longitudinal forces. And here's the main gear barrier. The longitudinal accelerations were uniform aft of station 460, peaking at plus 5.6 Gs and minus 6.7 Gs. This shaking caused no damage. A moment later, the nose gear collapse nearly doubled the G-forces in front of station 460. Still no damage. At the 6-degree slope, longitudinal acceleration in the nose peaked out at minus 24 Gs, with a pulse duration of 70 milliseconds. Peak longitudinal accelerations for the rest of the cabin were about minus 10 Gs. At the 20-degree slope, peak accelerations in the cockpit were minus 27 Gs. Shortly after impact, the breaking and crumbling of the fuselage at station 370 absorbed enough energy that acceleration peaks aft of the brake were about minus 10 Gs. Now let's shift to a head-on view to better see the vertical accelerations. Again, the same three impacts. At the main gear barrier, accelerations were generally moderate and cyclic. But the center of gravity registered a plus 43 Gs and a minus 54 Gs. This was only a local condition, not affecting the remainder of the aircraft. A moment later, the nose gear barrier impact. At station 195, the peak accelerations were plus 39 Gs and minus 31 Gs. Again, only a local condition. Contact with the 6-degree slope produced an acceleration peak of minus 30 Gs in the cockpit. Further aft, at the aircraft center of gravity, the cyclic accelerations peaked at plus 13 Gs and minus 19 Gs. Final impact gave cockpit readings of minus 45 Gs vertically. There were acceleration peaks of plus 7.4 Gs in the tail because of rotation of the aircraft after hitting the slope. As it pitched, the tail section hit the ground, resulting in peak accelerations of minus 50 Gs vertically, causing the fuselage to break between stations 1020 and 1030. Now, in order to relate the airframe acceleration loads with the loads on the experiments, let's locate them in the fuselage. The crew seats in the cockpit, the cargo experiments, passenger seating at the aircraft center of gravity, the litter experiment, and the aft passenger seats. These 5 experiments yielded oscillograph traces in both vertical and longitudinal directions. Analysis of the measurements revealed peak accelerations at the 3 obstacles. When the aircraft hit the gear barrier, the longitudinal and vertical accelerations of the pilot's seat were nearly identical to those of the cockpit floor. Stretching of the lap belt and shoulder harness reduced the acceleration of the dummy. This same condition occurred as the aircraft slid up the 6-degree slope. However, the dummy accelerations lagged behind seat accelerations by 80 milliseconds. At the 20-degree slope, the pilot's seat longitudinal acceleration reversed direction, indicating a seat attachment failure. But the dummy did remain attached to the seat and experienced a minus 18 G longitudinal acceleration for 20 milliseconds. Now recall the cargo restraint system. 2 rigid steel cargo pallets were installed, one with a rigid cargo, the other with a crushable cargo. Total weight of each amounted to 3,000 pounds. At the gear barriers, the longitudinal load for the rigid cargo is 6,600 pounds. For the crushable cargo, 17,300 pounds. At the 6-degree slope, a longitudinal load of 22,000 pounds for the rigid cargo, 41,400 pounds for the crushable cargo. At the 20-degree slope, even with a rise in acceleration, the cargo loads dropped. The rigid, 17,300 pounds. The crushable, 39,000 pounds. At the same time, there were maximum vertical loads of 22,000 pounds for the rigid cargo and 28,000 for the crushable cargo. And significantly, there was no failure of either cargo pallet or tie-down system. Recall the triple passenger seat located at the aircraft's center of gravity. During impact with the gear barrier, the dummy in this seat experienced about the same decelerations as the seat itself. At the 6-degree slope, seat longitudinal accelerations were only minus 10.7 Gs, but the dummy experienced an acceleration peak of minus 18.6 Gs. This was because of dummy rotation and the elastic seat belt. At the 20-degree impact, the dummy experienced a longitudinal acceleration of minus 13 Gs and a vertical acceleration of minus 18 Gs. The occupants of the two litters experienced at the gear barrier about the same longitudinal and vertical cyclic accelerations as those measured on the floor. They were, however, less frequent. At the 6-degree slope, the bottom litter dummy experienced peak vertical accelerations of minus 12 Gs. Longitudinal accelerations for both litter occupants were about the same. The 20-degree impact accelerations were less severe vertically than those on the 6-degree slope, but the longitudinal accelerations were alike. In the aft seat at the gear barrier, the dummy longitudinal accelerations lagged behind seat accelerations. Here, the aft part of the aircraft received a definite vertical peak acceleration rather than the cyclic vertical accelerations experienced in other parts of the fuselage. At the 6-degree slope, the dummy experienced its peak vertical and longitudinal accelerations at the same time. At the 20-degree slope, the seat belt stretched, resulting in a 100 millisecond lag between the dummy and seat accelerations. Basically, then, the selected experiments revealed a definite pattern of increasing forces. As the barriers increased in severity, the G-forces inside the aircraft correspondingly increased. First, the horizontal forces. At the landing gear barrier, peak horizontal accelerations on the airframe, the experiments, and the instrumented dummies. At the 6-degree hill, again even higher horizontal accelerations on the airframe, the experiments, and the dummies. And at the 20-degree slope, these horizontal loads continued to rise. Similarly, the vertical accelerations also increased during the test. At the landing gear barrier, vertical accelerations on the airframe, the experiments, and the instrumented dummies. At the 6-degree slope, the airframe, the experiments, the dummies. At the 20-degree slope, the airframe, the experiments, the dummies. The 5 experiments just shown are typical of the detailed information obtained in all 17 experiments. Information documented in Federal Aviation Agency Technical Report ADS 38. The DC-7 crash is covered by ADS 37. The data indicates that the crash was potentially survivable in terms of aircraft crash loads and structural integrity. Of special interest, the main cabin section, aft of the brake at Station 380, remained intact, with only negligible reduction in livable space. In this cabin area, the accelerations and velocity changes were not sufficient to cause a failure of either lap belt or seat. An analysis of the simulated fuel spray patterns shows a difference between the gelled water dyed red and the plain water dyed yellow and green. Most of the gelled water remained in the tanks through the crash impacts. It drained out slowly, forming a puddle at the base of the 20-degree slope. Because of these tests, the search is being pressed for ways of reducing or eliminating the vaporization of fuel in a crash. The field of gelled fuels may be the answer. The principle is shown in these tests of jet fuel samples impacted on a target which is provided with an ignition source. Here, at 2,000 frames a second, you see the speed at which flames spread throughout the liquid fuel. With only 1.5% of gel additive, this is the reduction. These varied research and development activities are vital continuing programs which represent the concern of your government through the Federal Aviation Agency for improving the airworthiness of all types of aircraft and increasing crash survivability. Our task has a single, constant objective: safer and more reliable aircraft. Instrumentation and a greater variety of experiments in the second test. As soon as the dust of the DC-7 test had settled, reduction of data began, and the results were incorporated in the Lockheed Constellation Model L-1649, which was being prepared for its crash. Shown schematically, the Connie was to accelerate down a runway jet. A key part of this effort, done jointly with industry and the military, involved crashing two worn-out civil transport aircraft as heavily instrumented test specimens into typical ground crash conditions. Many questions needed answers. How can survivability be increased? What are the loads and accelerations inside the aircraft during a crash? What happens to fuel when tanks are ruptured? The first test, the crash of a DC-7, demonstrated the feasibility of the test technique. It also encouraged the test engineers to include an even higher degree of Tomorrow's aircraft are almost here. In designing them, in planning their components, in testing them, aerospace engineers are faced with many new ideas and problems. The Federal Aviation Agency is, therefore, seeking to identify beforehand those improvements necessary to sustain an acceptable level of air safety. The engineers of FAA continually assess the technological limits of safety and aggressively seek out those advancements which offer significant promise. One of these reviews, which revealed many possibilities, was the Transport Crash Safety Project.